So now we are going to discuss how we can simulate the problem discussed as example 1. That is the standalone system. I just share the screen. So we have seen this problem. So we have to design a standalone PV system which will feed the 6-watt 12-volt lamp. So for that, we have designed the module requirement as 10 watt, charge controller as 5 ampere, and battery ampere hour as 5 ampere per hour. Now we are going to simulate this full system shown in block diagram, right? So this is blocking diode. If you want, you can put, otherwise no need to put it here. That is only for prevention of back current flow towards the panel. Anyhow, finally we are going to put a switch here, so there will be no backflow. There is no bidirectional converter, so it may not require now. So this is a 10-watt panel. In MATLAB, the lower wattage panels are not available, so we have to take the user defined and we have to give the specification by hours. Then charge controller. Here, instead of charge controller, we are going to use the buck regulator, because the charge controller is nothing but your DC regulator, right? Why I am using this buck regulator, I will explain. Then lamp load, we are going to emulate this lamp load by resistance. You see the next slide. For emulating this resistor, we know the voltage and power rating of the load. Voltage rating is 12, power is 6. So by using this relation P equal to V square by R, we calculate R as 24 ohm. So instead of this block, we can put directly 24 ohm resistor. Next, we have downloaded the 10-watt panel, which is market available. So 10-watt panel, the operating voltage will be 17 volt and operating current is 0.5. But we require 12 volt at the output to operate this lamp load. So as input voltage is greater than the load requirement, we are going for the buck regulator. So with this pre-introduction, I'm directly going to MATLAB. Here in MATLAB, I'll be taking the ready-made available module. I will tell how we can take. Due to the time constraint, already I simulated and opened this MATLAB file. But anyhow, I will take it from the library. You can search it for PV, it will come. Otherwise, you can go to the Simscape. Then we can go with electrical. Then there is a specialized power system. I think otherwise we can go with this renewable system block. We can have Simscape, then electrical. There we can check it out, renewable sources. Otherwise we can directly put PV array. So here it is there. It is in this electrical block. We'll be having the specialized power system. Here we can have PV block, right? We can drag and drop it here. Here, as I told already, you can see there are different panels are available, ready-made panels, but they are having higher ratings. I searched out, there is no low rated panel, so I have taken the user-defined block here, right? Here, I have to define the cells per module, open circuit voltage, short circuit current, voltage at maximum, voltage at current. This temperature coefficient may be common for silicon PV array. For feeding this, what I can do is, I'll take this PPT, this data sheet have been downloaded. So maximum power, it is automatically calculated in MATLAB. So I have to feed this maximum power point, voltage, current, open circuit voltage and short circuit current here. Okay. This only I have done in this MATLAB. So I double click. The same block I have redefined here, user defined. I entered 36, 21.6, 0.61, then 17.6, 36 also are in series. Okay. Then 0.57. This temperature coefficient I just leave as it is default. Okay. So as I'm after entering this, automatically it is come as 10 watt panel, right? Whether we will check whether we have get the same characteristic, you can check it here, plot. So under standard test condition, I'm getting 10 watt and 0.56 current. Okay. This panel I have taken here. So for demo purpose, I have taken, so I deleted this. So output here, I have put 1000 watts per meter square and temperature is 25 degrees C. And for measuring VPV, IPV separately, I can put this mux and taken here out block because I don't want to make here connections as a clumsy one. So I just always use go to and from blocks to connect the different ports. Then in output, I'll put a voltage probe, current probe. These two are same only, but while we are connecting the converters and other things after this, it will be useful the scopes. That's why I connect now itself. Then instead of making variable resistant to sweep the voltage of PV array, I have put the voltage control source. So here I have used a ramp to sweep the voltage so that I'll be tracing the characteristics from open circuit to short circuit. Right? I just run this. The same thing, whatever I'm getting inside, I'm taking outside because we have to take outside to make use of this to connect converter and inverter circuit. Right? Now I just check this VI characteristics. I'm using XY scope for tracing the VI characteristics. Right? Then VP characteristics. For this example, we are not going to vary any insolation or temperature, but anyhow, for this demo, I just put some variations here. I just change some 500 half insolation. I will run it out. You can see this characteristics wattage will be reduced. I just only open the VP characteristics. Okay. So we'll be getting the characteristics lesser than 10 watt, 5 watt, half watt. Okay. So once again, I'll change it. This is, you can similarly, you can define your own panel by feeding the data sheet of the conventional or market available panels, and we can simulate the required panel characteristics by feeding these parameters, right? So this is the PV panel selection. Next file, as I told already, as discussed in the PPT, by using the standard equations presented in the Rashid handbook, I am designing this LNC values based on the input voltage, output voltage. Here you check it. I use only 24 ohms for emulating the 6 watt 12 volt lamp load. Okay. Then I'm using VIN and IN scope input voltage. I'm putting the panel operating voltage. Then PWM generation, as it is a regulator to regulate to 12 volts. I have taken the actual voltage here, 12 volts as reference, and comparator can be used to produce the comparison and the error voltage. This error voltage is processed via this PA controller. There is availability of ready-made PA control block in MATLAB, but while interfacing a larger circuits, sometimes it creates problem. That's why I'm using gain and constant integrator block to realize PA controller. This is KP plus KI by S. This is your PA controller. I put it here. Then the processed error will be compared with the high frequency carrier wave. Even here I am taking carrier wave by generating, by using the repeating sequence. I generate this repeating sequence of 10 kilohertz, right? So this PWM pulses will be generated until it will be given to the buck regulator, switch in the buck regulator. So I will run this. So you can check it out. It is 12 volt and 0.5 ampere. If you are multiplying, it will become 6 watt. Okay. So this regulator operation, for explaining this, I can modify any voltage. So you can check 15 volt I will apply. It will regulate to 12 volt. But it's not our discussion point of view. Anyhow, I just explain as it is a regulated. I just tell you how it will be regulated, right? So whatever the input voltage changes, it will be giving this 12 volt supply. Okay. So I am putting some 20 volt or so beyond this 17 volt. I run it again. This outside is labeling I have done. So it is not changing, but inside I have changed it out. Okay. So it is giving. Okay. So that is for demonstration purpose. So I just once again coming back to 17.6 volt. So I apply it. Okay. Run it. I check it out. We'll be getting the 6 watt 12 volt. 6 watt by multiplying this. Okay. So this is where buck regulator as a charge controller. Next, we are going with interfacing this PV, whatever we have used as a file 1. Right, as I told already, the scopes are useful while interfacing this. This is your buck regulator. As we discussed in the theory online, theory in online mode of the first day, it may be a nonlinear source which will act as the current source as well as the voltage source. While interfacing with this type of application, we have to make it as a stiff voltage source. That's why we are putting the coupling capacitor here. Right, the buck converter, the rest of the things will be the same. In the buck regulator, I just replace the source by this PV array with coupling capacitor. Okay, so I'll run this. You can check. It is settling out. Okay, we will observe in voltage scope here. It is settling out. Then current scope here can go with auto scaling. So it is settling here. Okay, so we can close this window. This window also I will close it out. Okay. Now if I change the insulation to some 800, because as discussed in the very first lecture, around whatever the insulation changes, it did not much affect the VMPP voltage. Here we are not using MPPT also, because as we are deciding proper panel sizing, we may not require the MPPT. Let us check what it will happen when it is 800 watts per meter square. Check it out. It is providing the same conditions. Okay. Because why I am telling, this is 10 watt to 2 feet 6 watt load, right? So the less than 6 watt will come with very lower insulation. So around till 500, it will be supporting the load, right? It will be supporting the load. Okay. We will change this to again 1000 and keep the file. Okay. Now we have put PV array and charge controller. Next, we will see battery interfacing. Battery, what we have decided, 5 ampere hour, 12 volt. I'm putting 60% initial state of charge and battery response time is 30 seconds. Okay, but we are not going to run the battery for 30 seconds. So we may not see the discharging characteristics, but we can check whether this battery is supporting. I'll run this. As this value is displayed already, because already I run it, but again I will running. I'm running the simulation. So it is 12 volt and 0.5. We will see the impact of, I think it is running till, we will wait. So anyhow, already the voltage and current values are reached. So we will stop this. Okay. We will see the voltage scope. So it is settled. Okay. We can close this window. And next file, we can check the switching operation. Here you can, I put a switch, right? For some time, that is I'm putting this builder block, right? So up to 0.15 second, the PV array is connected to the load along with battery. This time battery will be charging. Load is getting power from the source. After that, this will be disconnected. So only battery will feed. Battery will feed. I am putting here. Battery is all time connected, but for showing the difference, I just put a lag here. So this time there is no source available to the load, 0.15 to 0.16. There is no source, either PV or battery is not available, just to demonstrate the impact of the battery connection, right? Till 0.15 second, the source is feeding load as well as charging the battery. 0.15 to 0.16, both battery and source is disconnected. But after 0.16, source is disconnected, but only battery is feeding load. Why I'm putting this is, we are not going to run for 30 seconds the battery, so we may not see battery charging and discharging current. That's why I just put this. So switch like this. So we will run this and see the waveforms. So we will see this voltage scope, anyhow 12 and 5. So till this you can see the ripples in the voltage because the source is feeding. For source has some little ripples, right? After that, there is no power feed from either solar PV or battery. After that, it is fed by only voltage battery. So battery voltage is stiff voltage. That's why it is like this. We can see the current now. Current scope. So here you can check it. There is no current during this period. Purposely, we are disconnecting both, right? So that's all about your first problem. So for making this block diagram realizable, first we have to define this PV panel. If it is ready-made available, we can take it. Otherwise, we have to redefine using this data sheet. Then charge controller, whether it is a step up or step down depends on that. For simple demonstration, I'll take basic converter. Here, either I plan to take boost or buck, but as this voltage is 17, I have to definitely go for buck regulator. I have taken buck regulator. Then for simulating this, I'm taking resistor value by calculating this 24 ohm. The battery, I have taken the ready-made block in the simulation and I have put this. For making the impact of battery connection, I'll just put this switching because only battery, if you want to see the impact of battery charging discharging, we have to run for a long time. It will come. That's why I just put a switch and immediately show the impact in the voltage waveform alone. But if you see the battery characteristics for running full time, then we can see the charging, and after that, after the switching, the discharging will take place, right? That will be there. So that's it about your example of the first simulation, first design problem.